Okay, good. So this is the continuation of where we stopped in our last class. And this is quite very, very important, you know. I wish we are able to complete it today, but if we don't complete it, I would add the completion. I will make the video and send it to the group. Okay, so here we have so many things to discuss about. I will try and be fast. So we are looking at phase changes. If you notice, we discussed latent heat, and we said that latent heat is the heat involved during phase changes. Can you remember? That is the heat involved during phase changes. That means phase change, like I described, is the change from one phase to another. Like you see, you have solid to liquid, we call that melting. We have liquid to solid, we call that freezing. Liquid to gas, vaporization. Gas to liquid, condensation. Solid to gas, sublimation. Gas to solid, deposition. Now, but the main thing I wanted us to know here is that, let me write this. As you go from solid to liquid to gas, the process you need to convert solid to liquid and liquid to gas is heat. You need heat. That means heat will be absorbed. Okay? Now, but to reverse back, if I want to go from gas to liquid, the only way I can achieve going from gas to liquid, which is condensation, is by cooling. So I'll write cooling here. The same thing from liquid to solid is cooling. So what this means is that the processes involved during phase changes are heating and cooling. Okay, let me write it in full: heating, then cooling. So heating is responsible for the transformation from liquid to liquid and from liquid to gas. Then while cooling is what is responsible to go from gas to liquid and from liquid to solid. I don't know if that makes sense. Hello, I need responses. You can unmute yourself. I can't hear you.
Sir, please come again. Sorry, you said the heating is from liquid solid to liquid.
No, what I said is that the process for going from solid to liquid or from liquid to gas is heating. That means it is without heat, solid cannot become liquid, and liquid cannot also become gas. Do you understand?
Yes.
Okay, good. Then if I want gas to turn to liquid, then I will need to cool. That means I will need to reduce the temperature. That would make gas automatically turn to liquid. If I continue the cooling process, then liquid will become solid. That's the reason why water can never become ice except you put it in a refrigerator. The job of the refrigerator is to cool it. It cools it to the point where liquid can no longer move. It just has to solidify to become ice. Does it make sense now? Response.
No, sir, it's somehow confusing.
Okay.
No.
Now, look at your pot, for example. When you go to boil water, let me say you have water, for example. If I need to change all this water to become gas, the only way I can achieve this is by heating it. When I heat water, it's going to, when it boils, as you keep heating it, it gets to a point it boils, then it gets to a point all the water evaporates to become gas. Have you ever forgotten water on fire, and when you come back, you didn't find any water again?
Yes. Yes.
That's heating. So heating is what that means is that all the water there has been converted to gas or vapor, as the case may be, or steam, as the case may be. And in the same way, if you want to go from gas, you need to get water from gas. all you need to do is to cool the environment. Now, try this on your own. Take out a bottle of chilled Coke from the fridge. Clean it very well. Make sure there is no water. Leave it on the table. After some time, you will notice that there will be water droplets on the Coke bottle. Where is that water coming from? That water or that liquid that is formed on the Coke bottle is because the Coke bottle is very cold. And so cooling means that the particles will no longer move as fast as they used to move. Now, let me tell you why this happens. Remember that solids, the particle of solids are very closely packed. Particles of solid do not really move like that. Then particles of liquids, there is a little space between them. There can be a little movement between them. Are you getting me? Then for gases, the space in gases is quite high. I hope you get what I'm saying.
Yes, sir.
Yes. So now, if I heat solid, for example, heating will make the particles to start agitating. They start agitating until their bonds break and they now become a little freer like liquid, because there is something that is holding solids together. Those intermolecular forces, it is heat that can break it down, because heat will cause it to vibrate until it melts and become liquid. And in the same way, if you keep heating the liquid, every particle keep looking for where to go, keeps vibrating until it becomes gas. So heating has a way of breaking the bonds between molecules and making it open up. And the more it's open up, the more it changes from solid to liquid, then to gas. Does that make sense now?
Yes, sir.
And in the same way, for gas, if I cool gas, the particle, one of the things we know gas particles for is that they move randomly. They are random in their movement. But cooling makes everything slow down. And as it slows down, if you keep cooling, the movement keeps slowing down until it gets to a point where gases will now condense to liquid, because the particles are now getting closer to each other. And as a human being, during hot season, you are more active. But during cold season, you're a little slow, you're a little cold, you're a little not very active. Am I making sense now?
Yes. Yes,
Yes.
sir.
So if they ask you, what is the process? How do I convert liquid to gas? The simple answer is heating. You heat. When you heat the liquid, it gets to a point, it becomes gas. And that's the same from solid to liquid. You heat. Or from solid to gas. You heat. But if the reverse is the case, like from gas to liquid, then you have to cool. From liquid to solid, you have to cool. From gas to solid, you have to cool. It reduces the motion. I hope that is clear now.
Yes, sir.
Yes, sir.
Okay, only one person is responding. So I'd already mentioned this, but this one actually talks about the effect of heating and cooling on phase changes. For example, let me start with this. From solid to liquid, that's melting. You see that heat breaks the rigid intermolecular bonds of the solid. Now, this is an exam question. So molecules gain energy and begin to move freely. So once molecules gain energy, they begin to move freely. The substance melts at a fixed melting point. And that's the same thing with liquid to gas. Further heating causes surface molecule to escape, that's evaporation, or all the molecules to gain enough energy to vaporize, and all of that. Okay, here it says between phase changes, added heat increases kinetic energy and raises temperature. Now, this is important for you to know. And please, I want to say this is a very common JAMB question. There is a relationship between kinetic energy and temperature, and that relationship is proportional. So proportional means that the higher the kinetic energy, the higher the temperature. That means when something is hot, it means that the kinetic energy is high. It is vibrating more, it is moving more. But when the temperature is low, the kinetic energy is also low. Don't forget that kinetic energy simply means the movement, energy due to motion. Okay?
Yes, sir.
Okay. So now temperature stays constant. During a phase change itself, all heat energy is used to break bond and temperature does not rise. I've already mentioned that during the phase change, temperature does not rise. And you come back here, effect of cooling from gas to liquid, we call that condensation. If you remove heat, removing heat slows gas molecule. Are you seeing? I mentioned that. The slow gas molecule, they lose energy and come together as liquid. So condensation occur at dew point or boiling point, the reverse. That's, by the way, we will still learn more of that. Now, further cooling, if you keep cooling that liquid now, further cooling causes molecules to slow until they lock into a rigid lattice structure. The substance freezes at its freezing point. And I've told you, freezing point is the same thing as melting point. We'll talk about that later. So the same way you say the melting point of ice is 0 degrees Celsius, that's the same way you will say the freezing point of water is 0 degrees Celsius. Don't forget that. So cooling simply means temperature drop. And you can see here that between phase changes, heat removal decreases kinetic energy. When you remove heat, to remove heat means to cool. When you remove heat, then the kinetic energy also reduces and that lowers the temperature. Very, very important. And like we say, temperature remains constant during phase change. So during a phase change, heat released comes from bond formation. Temperature stays flat until all the molecules have changed state. So this is a very, very important thing for us to note. So as you go from solid to liquid to gas, you need heating to achieve that conversion, that transformation. And as you go from gas to liquid, then to solid, you need cooling to achieve that. And these things are things we do at home. So it's our daily experience. Are you with me?
Yes, sir.
Yeah, and I also want to mention something here. In the case of cooling, have you ever noticed when you come out in the morning, you notice water droplets on the car, on the grass, on clothes outside? You just notice water on top of a lot of things. The reason
Yeah.
for those water
Yes.
droplets is because of in the morning is very cold. So that being cold favors condensation. That means it is cold that gas now turns to liquid. Those are those water droplets you see all of those places. So this is the effect of heating and cooling in each of these substances. Am I making sense?
Yes, sir.
I need to hear other people's voices. Is the only one person that is in this class? Hello, where are the other voices?
Yes, sir. We are following you here.
Okay, good. So that now leads us to what we call Newton's laws of cooling. This is an important law, this, but nothing much. You're not going to do much here, but at least you should know it. So the Newton's law of cooling states that the rate of heat loss of a body is directly proportional to the difference in temperature between the body and its surrounding, provided this difference is small and the surrounding remains at a constant temperature. That is the law. And this is the mathematical representation of the law. That means this, when you say negative dq over dt, that negative dq over dt talks about rate of heat change, the rate at which heat changes. And we say K here is a constant, the cooling constant, then T minus T naught. This is your T naught here. If you notice, we have it here. It is the surrounding temperature, the temperature of the surrounding, and capital T here is the body temperature. The most important thing you should know based on this formula is that the rate at which heat change is affected by the change in temperature between the body and the surrounding. Meaning that, okay, let me give you an example. Have you ever come out from a room that is very cold, air conditioner, and you really felt the cold, but immediately you came out and met the outside world, everywhere becomes very hot? Have you had that experience?
Yes, sir.
Yes.
Okay, so that experience simply means that the environment, the temperature of the environment is different from the temperature of the body. And so the rate at which the temperature, the heat, and remember that heat can only be transferred because of the temperature difference between two bodies. So the rate at which heat energy is transferred is dependent or is determined by the difference in temperature between the body and the surrounding. Now you can see the conditions. Number one, temperature difference between body and surrounding must be small. It must not be too large. That's very important. That's for this formula to hold. Number two, surrounding must remain at a constant temperature. That means the surroundings temperature should be constant. Then number three, heat loss is primarily by convection or radiation. Most importantly, this Newton's laws of cooling is only true for convection and radiation. Now, the next thing I want to talk about is what we call the cooling curve. Now, I don't have the cooling curve here, but I am going to draw it for you guys. The cooling curve simply is a curve that shows how substances gets cooled. Now, and watch this. You are going to see this. If you are conversant with exam questions, you would see things like this. Let me start with steam. Let me start with steam at 150 degrees Celsius. Once you see 150 degrees Celsius for water, it's no longer water, it is steam. At 100 degrees Celsius, water begins to convert to steam. So anything above 100 degrees Celsius is now called steam. So here now, I will call this steam. This is the temperature of steam. Now, as it keeps cooling means the temperature keeps reducing. It now gets to a point where at 100 degrees Celsius, the temperature will keep reducing, but once it gets to 100 degrees Celsius, it will stop reducing. It will remain there until all the gas has fully condensed. We call this condensation. Now note this, because they can draw the diagram and make here X and ask you what is X. The X here is called condensation, as long as it is coming from 150 degrees Celsius. Once it gets to 100, it starts condensing. Are you seeing that? And this process of condensing, hello, are you following what I'm saying?
Yes, sir.
This process of condensing will now change the steam now to water. At this point, it is no longer, at this point, it was still steam, but immediately it got to this point, it is now water. Because if it keeps cooling, once it gets to 100 degrees, the temperature will not change. It will remain the same until everything has been turned to water. Now, if the cooling continues from this point, it will keep reducing. It will keep reducing until it gets to here where the temperature is 0 degrees Celsius. Are you seeing that? 0 degrees Celsius. You know, these are very important temperatures in water. Once it gets to 0 degrees Celsius, guess what? The water will start freezing. So this will remain the same for a long time. This process now is called freezing. The temperature will not change at this point. Once all the water, at this point it is water, but once it is done freezing, it is now called ice. At this point, it will reduce again and keep going. So this is what the cooling curve looks like. In a cooling curve, always watch out for condensation and freezing. In a cooling curve, always watch out for condensation and freezing. Anything from 100 degrees Celsius, you know it is condensing because it's coming from gas. Anything from 0 degrees Celsius, you know it is freezing because water is freezing to solid or to ice. I like to hear from everybody. I hope this makes sense.
Yes, sir.
Yes, sir.
Yes, sir.
So you can write up here, this is cooling curve. We call this cooling curve. Okay. Then we have, okay, I need you to draw this quickly so that I can continue with the next. Or you can simply screen grab it, so that you can draw it later. Okay, so I want to take this away. You can always look at it later, or maybe you have screen grabbed it. So I want to rub this off. Okay, so now at this point, this now leads us to what we call heating curve. Heating curve is the reverse of cooling curve. In heating curve, the temperature is increasing. So this is what I'm going to have. And here, let me start with, let's say, ice at, let's say, negative 15 degrees Celsius. So when you keep heating ice, the temperature will be increasing. It will increase until it gets to 0 degrees Celsius. This is 0 degrees Celsius. Once ice gets to 0 degrees Celsius and you keep heating, it will melt. The temperature will not change. From this point to this point, the temperature will not change. This process here, we call it melting. Then once you keep applying heat, guess what? This guy will keep increasing again. Once it is done melting, remember, everything must melt before the temperature rise. During that period of melting, there will be no change in temperature. Okay, so from here now, once everything is done melting, the temperature will keep increasing. It keeps increasing until it gets to another temperature, let's say at 100 degrees Celsius. Once it gets to 100 degrees Celsius, of course, you know what happens. It remains the same again, because at this point now, vaporization is occurring. The liquid now wants to turn to gas, steam. Okay, so at this point, we call here vaporization. So it is when all the liquid has finished vaporizing, then this can now continue to increase. So this is called the heating curve, which is different from the other curve, which we call the cooling curve, curve, RV. So I hope this makes sense. They are not saying anything.
Yes, sir.
Okay, good. So I want to proceed from here. I want to proceed. So we have to go back. You can always get this later. So now you know there is heating curve and there's cooling curve. Now, the next thing I want us to talk about now is to now discuss the different phase changes. The different phase changes. And the first one we are going to look at is called evaporation. Evaporation. This is one of the process of phase changes. Now, I want to note here that evaporation is not exactly the same thing as vaporization. One of the major difference between evaporation and vaporization is that evaporation of liquid can happen at any temperature. That means at any temperature, liquid can easily evaporate. There are things that can make liquid evaporate. We are going to discuss that here. But vaporization only happens after the liquid has boiled. Then after boiling, all the gases now vaporizes to become steam or vapor. I hope that makes sense.
No, sir. Sir, please repeat.
Okay. Now, I was trying to talk about the difference between evaporation. There's a difference between evaporation evaporation, and vaporization in this sense. Now, one major difference is that evaporation can happen at any temperature. A good example is if you pour water on the floor, for example, after a very long time, maybe after a day or after 2 days, will you still see the water on the floor?
No.
You did not apply any conscious heat. There was no conscious application of heat. So there would be no direct evaporation. I don't know if you understand what I'm saying.
Yeah.
Yes, but in the case of vaporization, is when this one happens when you are heating water. Maybe you put water on fire. It gets to a point where that water boils. Then after boiling, immediately the water boils. If you keep heating, all the water will now be converted to steam, what you call steam, or what we call vapor. You know, both vapor or steam are all called gases. They are all gases. So vaporization does not occur until after boiling. But evaporation can happen at any temperature. It can happen in the afternoon, can happen in the evening, can happen at cool temperature, can happen at hot temperature, because different things can make liquid evaporate. Am I making sense?
Yes, sir.
So
Another case of evaporation, let's take example, you take your bath, for example, you are wet, but when you start running, after some time, what happens to the water on your body? It dries up. It dries up, right?
Yes.
yes.
Without you heating it, there is no heat. You did not consciously, it did not boil. Because if it boiled, your skin will not remain the same. Your skin is going to damage. It just evaporated. But in the case of vaporization, you must boil the liquid. The liquid must boil before it now turns to gas. That's the difference between evaporation and vaporization. Am I making sense?
Yes,
Yes,
sir.
sir.
Good. So now you can see, I even wrote here because in exams, you are going to be very concerned about the difference between evaporation and boiling. But let's see this statement here. It says, high energy molecules at surface escape into the air, leaving behind low energy, cooler molecules, which is why evaporation causes cooling. Now, this statement is a very, very important statement. So you may need to write that evaporation always brings about a cooling effect. Evaporation always brings about a cooling effect. That's the first thing I want you to note. Evaporation always brings about a cooling effect. I'm going to explain that. Then the second thing I want you to also note is that evaporation is a surface phenomenon. That means it's only the water on the surface that evaporates first. Now, let me explain the first one, that evaporation always brings about a cooling effect. Now, have you ever put spirit on your body? Spirit, that's, spirit, alcohol on your body.
Yes, sir.
Yes, sir.
What do you notice when you put it on your body?
Gives this cooling effect.
It gives this cold sensation, right?
Yes.
That cold
Then-
sensation is because the spirit is evaporating. Anytime evaporation happens, the cold sensation will always be felt on your skin. Hello, are you with me?
Yes, sir.
Evaporation is the reason why after you finish taking bath in the morning, you start feeling cold. The reason for that cold is because the liquid in your body is trying to escape. And anytime they escape, cooling, the rest of the body will be cooled. And there's a molecular explanation to that. Let me explain that quickly. Now, when the surface, the liquid molecules on the surface, all the liquid have what we call kinetic energy. Let's say this is the container here. Okay. Now, all of them we have what we call average kinetic energy. The word average is because all of them don't move at the same speed. At least some will be slightly higher than others, and some will be slightly lower than others. But some of them will have enough energy to escape the surface. Some may have enough energy to escape the surface. It's just like, you know, you have a parent gives birth to 5 children, but I can assure you that those 5 children are not going to be exactly the same. Some may be more stubborn, some are less stubborn. Am I right?
Yes, sir.
Then there is a possibility, but God forbid, there's a possibility that one that is stubborn would escape from the house and run away from the house, maybe to go and visit friend or something, because the kinetic energy is high. That's exactly what happens here. Some liquid molecules have higher kinetic energy than the average kinetic energy, so they can escape easily from the surface of the liquid. If anytime liquid molecule escape from the surface of the liquid, the remaining liquid, their average kinetic energy will lower. And anytime average kinetic energy lowers, it means that temperature also lowers. Don't forget, initially I told you that there is a relationship between kinetic energy and temperature. Anytime kinetic energy is high, temperature is also high. Anytime kinetic energy is low, temperature is also low. So the only thing that can reduce the kinetic energy of a liquid body is when some liquid have escaped from the surface, then the average will reduce. Let me give you an example. When that stubborn child, if there is a stubborn child in the family, escapes, maybe goes to visit, wouldn't there be a bit more peace at home?
Yes, sir.
No shouting. Yeah, you guys may miss the stubbornness, but you will notice that that period, you say, Kai, this person is not at home. You can see peace everywhere. That's exactly what happens here. Once those ones that have high kinetic energy escapes, the remaining will calm down. And calming down simply means that their temperature is lower. That's when it becomes cold. And you may be wondering, why are we studying this? This is the reason. This evaporation is what they use in creating things like refrigerator. That's your fridge, your what is it called now? Your freezer at home. It's evaporation. When you put something in the fridge, it comes out, it becomes cold, and you'll be wondering, how does it become cold? It's evaporation. There is a liquid that runs through, they call it gas. It must be something that evaporates very faster, because the faster it evaporates, the cooler it becomes. That's the principle they use in creating fridge. Now, another example, this one now, some of you will know it, especially if you have grown in the village before. They used to have this, and this is an exam question, or is a JAMB question. They used to have this calabash where they put water and they cover it. Some people even dig hole and put the calabash inside. After some time, when you come to drink water from the calabash, my goodness, it's one of the sweetest water you can ever drink in your life. It's very chilled, very cold. Has any of you experienced it? You know, Gen Z, I don't know. Has
Yes,
any of you experienced what I'm talking about?
No, sir.
yes, sir.
Okay, so we have people that have visited village. Okay, so that cooling, the reason why it cools. Now, if is an exam question, why is it that water, when placed in a clay pot, cools after some time? The very simple answer is that because water molecule evaporates through the pores of the clay pot, evaporate through the pores of the clay pot. That's the answer. Another question can ask you is, how do clothes dry? That means when you put clothes outside, how do they dry? It's very simple. The process by which clothes dry is by evaporation. Without evaporation, clothes will not dry. That's the reason why during Harmattan season, you notice that evaporation occurs very fast. But during wet season, when the environment is wet, clothes does not dry fast. Why? Because evaporation is very slow during rainy season, but very fast during Harmattan season. I hope I'm making sense here.
Yes, sir.
So I've been able to explain that evaporation is a surface phenomenon, and I've also been able to explain that evaporation always brings about a cooling effect. That's an exam question you should not joke with. So let's go back to our slide. Now, This is comparison between evaporation and boiling. Now, look at this. Evaporation occurs at any temperature. I've mentioned that. Boiling happens only at a fixed temperature. For example, water can only boil at what? At 100 degrees Celsius. Abby?
Yes.
Then, yes, evaporation also happens only at the surface. I've mentioned that evaporation is only a surface phenomenon, but boiling happens all around the liquid. When water is boiling, everywhere is affected, everywhere is bubbling. Okay. The third one again is that evaporation is a slow and gradual process. Boiling is a rapid and vigorous process. Another one is that evaporation causes cooling of the liquid. I've mentioned that, right? There's always a cooling after evaporation. But in boiling, the temperature remains constant. It will remain constant until the liquid has boiled off. Now, finally, in evaporation, no bubbles is formed. But in boiling, there are bubbles that are formed. You know bubbles. When water boils, you start seeing bubbles inside the water.
Yes.
Am I making sense? Yes. So these are the differences between evaporation and what? And boiling. Okay. So these are exam questions. Take them seriously. Then the other part, which is where we are going to end today because of time, the extra videos I will make them and post so that you guys can follow because we have limited time. This one talks about the factors affecting the rate of evaporation. Number one is temperature. Now, this is an exam question, so take them seriously. One of the factors that affect rate of evaporation, that means how fast evaporation happens or how slow, is temperature. Evaporation happens faster when the temperature is high. High temperature, faster evaporation. More molecules, because the higher the temperature, the higher the energy molecules gain, and the more they can be able to escape the surface of the liquid. Now, the second one here is surface area. Large surface area, whenever there is large surface area, molecules can escape easily, and that makes it higher rate of evaporation. Now, let me tell you something about surface area. Have you ever, whenever you wash clothes and you squeeze it, do you notice that you usually spread it before you spread the clothes before you hang it on a hanger? Have you observed that?
Yes, sir.
Yes, the reason why you are spreading it is because you are increasing the surface area. When you finish squeezing clothes, you won't just carry it and go and put there. The clothes may not dry even after 3 days, or maybe at the end of the day, even if it dries, it will take so much time before it dries. So you need to spread it. The reason why you are spreading it is because of surface area. So the larger the surface area, the higher the rate of evaporation. Then the next one is the nature of liquid. Now, when we say nature of liquid, some liquids by nature evaporate faster. Like water. Can you tell me between water and fuel, petrol, which of them evaporates faster?
Petrol.
Petrol.
Petrol evaporates faster because by nature it evaporates faster. And if you put water and petrol on your skin, which one are you going to feel cool? Which one is going to feel cool more?
Petrol.
Of course, petrol, because the higher the rate of evaporation, the more cooling effect you are going to feel on your skin. I hope I am making sense here.
Yes, sir.
Okay, so another thing that increases rate of evaporation is wind, air movement. Yeah, so the more wind, the more evaporation happens faster. Whenever there is wind, there is more drying happens, in a faster rate. So wind is another thing. Another thing again that affects the rate of evaporation is humidity. Humidity. Now, somebody may ask, sir, what is humidity? Humidity is simply how dry or how wet the air is. Hear me again, dry or how wet the air is. In Nigeria, during the Harmattan season, the air is dry. That means evaporation will happen faster. Clothes will dry faster. I remember in those days, you can even, in such periods, you can even dry your clothes, wash at night and dry. The next morning, your clothes will be ready to wear. I'm sure you know what I'm talking about. In such cases, the humidity is very low. That means the air is very dry. But during rainy season, for example, the air is cold. The air is, not cold, the air is wet. And so anytime the air is wet, evaporation will be very slow. That's the reason why clothes find it difficult to dry when the air is wet, when it is rainy season. You can't dry, it struggles to dry up during rainy season. Hello, am I making sense?
Yes, sir.
Yes. Then another factor is pressure. So lower atmospheric pressure means lower boiling point, and lower boiling point simply means faster rate of evaporation. Later, I'm going to let you know how pressure affects boiling point. It's part of this topic because we just have to stop here because of time, but I will be posting them so that you can go through them yourself. Now, these are the factors that affect rate of evaporation. Yes, and I think that will be it for today. This one, don't worry about this. I wanted to talk about the experiments of cooling, but I already mentioned that, so no need of going into that. So at this point, if you have any question, you can ask very quickly before we come to the any questions? Okay. I can say that if you have any questions, you can drop it on our group chat. We can continue there on our group chats. That would help us. So I think that will be it for today. We have tried. I'm going to be dropping some questions on what we've learned on the group so that you can test yourself and see how well you're doing. Is that clear?
Yes, sir.
Yes, sir.
Okay, thank you very much. Also expect the video complete because I don't want us to go back to this topic. So I will be posting the videos for boiling, for condensation, for melting. Those are very important topics. So expect the videos maybe by tomorrow, by God's grace. Okay, so have a nice day. Okay,
Thank you, sir.
Thank you, sir.
you are welcome. Bye-bye.
Bye-bye.